Hello and welcome to our discussion of work, energy, and simple and complex machines. We began our discussion of force, and we've learned that force equals mass multiplied by acceleration. Then we derived that acceleration equals velocity divided by time. Therefore, mass multiplied by velocity divided by time will give us force. Then we learned about momentum. We learned that momentum equals mass multiplied by velocity. So if we have the acceleration, we divide by the time to get the velocity, multiply that by the mass of the system, and that will give us the momentum. Today, we're going to learn about work energy and how the simple machines are able to reduce the force expenditure that we must do, but they do not affect the work. So, for example, work is the capacity, work is energy is the capacity to perform work. If you have no energy, you will not be able to accomplish the work. And work equals force multiplied by displacement. So if you have pushed a cart 5 meters with a force that was 10 newtons, 10 Newton force multiplied by the 5 meters, that will come out to 50 joules, and the joules is the unit for work. So let me write that down. We learned that we have learned that work will equal force, force multiplied by displacement. So if I am pushing a cart with, we said the unit for force is newtons. We're pushing a cart a distance of 5 meters to the north or to the south or to the east, doesn't matter. But 5 meters, that's going to be put in where D is, so 5 meters. And the force is 10 newtons. So we multiply 10 newtons by 5 meters, the work unit will be 50 newtons meter, also known as, we said instead of Newton, we say since the unit for force is mass times acceleration, we can have kilograms multiplied by acceleration is meter per second squared. And we know that force times distance, and that's going to come out to force times distance. Force times distance is the same thing as work. So the distance was 5 meters, 5 meters, and the force was 10 newtons or 10 kilogram times meters per second squared, and that will come out to 50, all of that, 50 kilograms, 50 kilograms times meter per second squared times meter, which is the same thing as meter squared. So we can have kilograms times meter squared over second squared, or kilograms times meter per second, all to the power of 2. Or to help make life easier, they decided to call all of this unit, to call all of that, instead of saying newtons times meter, just say joule, joule. So when you say joule, that is the unit for work. That is the unit for work. So 50 joules. But remember, joule is the unit for work, and work has to be force times distance. Force multiplied by distance. And here we said the force was, for pushing the cart, was 10 newtons multiplied by 5 meters, and that comes out to 50 newtons meter or 50 joule. Okay, And this is our good friend, Joule. This is um, the physicist James Joule, who was able to devise that work equals force multiplied by distance or displacement. So what's happening here in this roller coaster? We change energy. Energy is conserved. It just changes from one form into another. We said that when you start your car engine, what happens? When you start the car engine, the gas that you got from the gas station, that's chemical energy, the gasoline. Then a combustion will happen, when you turn the ignition, then the fire of the combustion engine, that fire will cause the gasoline to ignite. So an explosion will happen. So now you have converted the chemical energy into thermal or heat energy. This heat energy will now push the pistons in the crankshaft, and that's now going to cause the piston to start rotating the car wheels. So now you go from heat energy into mechanical energy, and then you have kinetic energy, the energy of motion. So now you see that we have shuffled energy from gasoline, chemical energy, into combustion, heat energy, into mechanical energy, which is manifested in the form of kinetic energy. So kinetic energy is the energy of movement, known as half times the mass of the object multiplied by its velocity to the power of 2. So that is kinetic energy. There's also another type of energy known as potential energy. Potential energy is very important. Potential energy is the energy that the body has and is able to convert. So, if you have $100, that $100 has potential to be converted into euros, can be converted into peso, can be converted into pounds. So when the roller coaster is way up in the mountain, it has the potential to drop and have kinetic energy, roll, slide down. So the kinetic energy is not, the kinetic energy is half mv squared, but the potential energy is not half mv squared. That is kinetic energy. The potential energy is the mass of the object multiplied by the gravity constant, the acceleration of gravity, 9.81 minus 9.81, and then you multiply by the height. So if you have a bowling ball at the top of Mount Everest, that's 5,000 meters. Then another mountain, 4,000, then 3,000, then 2,000, then 1,000. So their height is different. And the bowling ball has the same mass and the gravity is the same. But each bowling ball, because it's at a different mountain, at the peak of different mountains, the higher the mountain is represented by the letter H, the height. So we multiply for the first bowling ball at the top of Mount Everest, we multiply 5,000, the height of Mount Everest, multiplied by gravity, minus 9.81 multiplied by the mass of that bowling ball. Then we can do the same thing for the other mountain that is 1,000 meters less. So 4,000, then there's 3,000, then there's 2,000, then there's 1,000. So you see that the potential energy increases when we increase the height. But as the roller coaster drops from that peak into the ground, what happens now is we convert that potential energy into kinetic energy. So no matter how you move a TV to the fourth floor, that's the fourth floor, the amount of work performed and the potential energy is the same. So you still gotta raise this TV to the fourth floor. So let's say each floor is maybe you have to climb 10 meters. So 10 meters, 10 meters, 10 meters. The height is 30 meters. So the energy you need to get up here is 10 meters times gravity times the mass of the TV. Same thing, the little girl here is using a pulley. So the pulley is able to lift this TV faster, but it does not at all affect the expenditure. So we need 30 times gravity times the mass, whether you are here using a pulley or not. But the only difference is These machines, that's why the title of today's lecture is Work, Energy, and Simple Machines. The machines, what they do is they do not reduce the work you need to do. The work is the same. But remember, work is force times distance. What they do, these machines, is they reduce the force you need to expend. Here, because we're not using any machine, we have to exert the exact force on the same distance. But in this machine, the machine is gonna use a different distance, like an enzyme. They're gonna use a different route, a different system, a different distance, but it's gonna keep the force the same. So we have to have a good understanding of what is the kinetic energy. The kinetic energy is the represented by half equals, let me write that down, kinetic energy. The kinetic energy equals half 0.5 times the mass of the TV you need to carry times the velocity at which you're carrying the TV to the power of 2. That's kinetic energy. Potential energy is going to equal, so kinetic energy is half mv squared, 0.5 times m, the mass, multiplied by the velocity to the power of 2, to the power of 2. While potential energy is mgh. mgh is the mass multiplied by gravity multiplied by the height. So if we need to take the TV up to 30 meters, so we multiply the mass of the TV multiplied by the gravity constant, 9.81 minus 9.81, multiplied by the height at which we need to carry that object. There's also an understanding of what is the power. What is the power? Power is the rate of work performance. So power will equal work divided by the time. And we already know that work is the same thing as force times distance. So we can divide force times distance by the time, and that will give us the power. So the power is the rate at which work is being done. So in any problem, if you're given the mass, the acceleration, and the displacement, and the time, you multiply mass times the acceleration times the displacement to get the work, divided that by the time. So your power is the frequency, your ability, your rate at you doing work. Okay, if you are able to in the same amount of time do more work than somebody else, then you definitely have more power. At the same amount of time, if you are less able to accomplish the same amount of work compared to somebody else, then you definitely have less power. That's the concept of power. So as we said, the potential energy does not change whether you're using a simple machine or you are carrying it yourself. But the machine would help you by reducing here, by reducing this height, by reducing the, we understand already that force is mass multiplied by the acceleration. So the machine can help you, the mass cannot change, but the machine can help you reduce the distance, reduce the acceleration, and that will help you, and change the time, and that will help you have more power. So they do not change the overall expenditure. The work is the same. It is just how we change the force. So they help us to expend, these machines help us to utilize less force over a longer distance. But here we're not doing that because we're just following the same basic formula. Force equals mass times gravity, and then work is mass multiplied by gravity times the distance that we need to climb up. But this does not mean even if you go up and down carrying the TV, you made a mistake, you thought it was the second floor, then you picked it up again, you went to the third, then you went back to the first, then we went back to the fourth. We're not talking about the work you did. We're talking about the work required to bring up this TV up to the fourth floor, which is 10 meters each floor. 10 times 3, that's 30. 30 meters multiplied by the mass of the TV multiplied by gravity. And that will give us the work. So this is James Watt, who discovered, so Watt is the unit for power. And we know power equals force. Power equals force times displacement. So the unit for that would be newtons times meter, which is the same thing as, we know that divided by time. So the power is force times distance, that's W. So the power is work divided by time. And we already know that work is force times displacement divided by the time. And then we have force times displacement divided by the time. And we already know that force times displacement is in the unit. Force is newtons, displacement is meter, and the time is seconds. So that's the unit for power. And we also know that this here could be represented joules. Work is known as joules. So we can have power equals joules per second, or this entire unit here, joules per second, can be rewritten as watt, after James Watt. So watt is the unit for power. Now these machines are very important because they utilize a way that does not decrease the work. They just decrease the force that you need to spend or the distance that must be, that the work needs to be applied upon, but they do not change the work. So if you look, for example, at this, if you look at this roller coaster, we said that the potential energy at the top here equals m times g times h. M is the mass of the system, the mass of the roller coaster, these 4 carts and the people who are in them. So the mass, let's say the mass is 500 pounds. 500 multiplied by gravity minus 9.81 multiplied by the height, the peak. So this is our potential energy. When the roller coaster drops, potential energy starts to slowly shift from the form of potential energy into motion energy, known as kinetic energy, until we hit the bottom here. And now we have 0 because the height is 0. Here we have no height. So here we had a little bit of height. We had midway here. So the potential energy is almost halfway here. When you have height 0, here you have 0 potential energy, and here you have 100% kinetic energy. Here you have 100% potential energy, 0% kinetic energy. In the middle, you have half potential energy, half kinetic energy. All the way in the bottom, you have completely kinetic energy and 0, no potential energy. So these are the simple machines like the pry bar. That's a type of a lever. And this seesaw that we see here, it must be comprised of a fulcrum. A fulcrum is this pivot center, this triangle here, this corner point here that will enable you to do the work. There is an FR and an FE. What does FE and FR stand for? FE is the effort force. That is the force that you apply in order to lift the object, this object right here. And the distance from where you apply the force right here with your arm, with your hand, so is where you apply your effort force, that's FE. The distance from where you apply your effort, FE, to the fulcrum, to this center is known as LE. The length at which the effort force is being transmitted to the fulcrum. Then at the other end, you have the resistance, this nail that is resisting you. This is the force of resistance. And the distance between the force where resistance is applied to the fulcrum is known as LR. So this length that is transmitting the force of resistance is known as LR. And the length transferring the force of effort is known as LE. And the closer the fulcrum is to the center, the resistance force, the more force will be transmitted. Think of it as a baseball bat. If you hit a baseball with the tip of the baseball bat compared to the middle of the baseball bat, where do you think more force will be? The force will be the farther you are away. The farther that you are away from the center of your the farther you are away from the effort force center, the stronger the force will be. And also the fulcrum, the closer the fulcrum. So for example, if this triangle moves to here, for example, I promise you, this nail will be out in no time, But if the fulcrum moves closer to you, imagine now you have to pluck off, remove this nail, but the fulcrum is not here. The fulcrum is up here. Imagine how much force you have to tip here while your triangle is here, and you have to remove the nail from here. Obviously, the longer LE, the longer the length on which the effort force is applied, the more force the more force the resistance will put up with. So the resistance here, if this is a baseball bat, the resistance is the baseball. So the baseball is going to hit this tip, and you are holding the baseball bat here. So the harder you hit the ball with the tip, the more the ball is going to fly and shoot off. This is a pulley. So there's another concept known as the IMA, the ideal mechanical advantage. The ideal mechanical advantage equals the length of the effort arm, this one here, this length, divided by the length of the resistance arm of the lever. So so for example, if I had a fulcrum like this, I wish there was another diagram where the triangle moved a little bit down. So on the second diagram, you would have the triangle moving closer to FR, the resistance force, and LE would be longer. So the longer LE, the more IMA we have, the more ideal mechanical advantage we have. So for this pulley, obviously this is not a lever anymore, this is a pulley. So the pulley has two circles. One is the axle that spins with the circle. So you have a rope on the outside, you rotate the really big circle to which is attached this little circle with the axle attached to it is this force. And the advantage is conferred with the longer the outer radius is. The bigger the outer circle is, the easier with which you'll be able to carry and pick up this resistance force that is fighting against you. You see, you're pulling this way and the force is pulling down with the ground. So the bigger the circle, the bigger capital R represents the radius for the blue circle, and little r represents the radius of the axle. So the bigger the circle on which you have your rope, the more with ease you're going to be able to pick up this resistance force that is attached to this little circle. And both of them are on an axle, they spin together, one for one. So an inclined plane is shown on the left and a wedge is on the right. So if this is a knife, the longer the knife, the sharper it is, and the more it will be effective in cutting. That's why the sword is the ultimate cutter compared to like a box cutter that is really, really small. An inclined plane. So here, if you want to know the mechanical advantage, the longer the knife, the longer the sword, the better it is compared to this handle length that you're holding it from. So that the ideal mechanical advantage for the wedge, a knife is a form of a wedge. the ideal mechanical advantage for a wedge is represented by the length of the wedge compared to this length of uh, this length of the handle that you hold it with. And also when you look at an inclined plane, the longer the inclined plane, the harder is it for you to push up this the more you're going to push up this, the harder will it be for you to push this object. So the mechanical advantage is always the length divided by this height. The screw shown, this is a screw here, is shown to lift very heavy objects. So like the corner of a car or a house, a short distance. So for example, if you want to change the car tires, what happens is you spin the fulcrum, and that will be able to transmit a force that pushes the car upward. So the ideal mechanical advantage is always proportional to the length. So the longer the lever on which you put your arm here at this tip and you start spinning and spinning, the longer it is, the more force with which you'll be able to spin this screw, and the more the screw will push upward. An ideal mechanical advantage is inversely proportional to P, and P is the space between these objects that help you push up the car. So if you look at this formula, everything at the top will help the ideal mechanical advantage, the ideal mechanical advantage. So the length here, the longer the length, the better the ideal mechanical advantage. And the longer P, the lower the ideal mechanical advantage. Here, the longer the length, the better the ideal mechanical advantage. And the longer the height, the less the ideal mechanical advantage. Here, the longer the length, the better. And the shorter the height, the less energy we need to expend. So length horizontal is not going to matter. Is not going to affect horizontally, is not going to affect the work, because work is only relying on M times G times H. It's not times width W, it's times H. So the shorter H, the less work the less work we have to spend. So that's why an inclined plane is helpful, because it divided for you this height into, so like for example, you cannot throw this box to the top of this height. But if you have an inclined plane, you have divided this height into smaller segments, and you keep going step by step until you have paid in full all of this energy requiring you to lift the object to the top. Same thing with the knife. The knife begins with this height, and then it decreases. So the longer the height, the longer the length, the more part of this sharp blade that's going to be able to be in contact with the object you're trying to cut. Here, the longer the radius of the big circle, the more mechanical advantage, and with less effort you need to push, you need to pull, you need to overcome this resistance. But if the small radius increases, the harder with which you'll be able to pull this pulley.